Dear students, now we are going to talk about yet another type of adjustment made in astronomical telescope. What we do is we let the final image to be formed at least distance of distinct vision. How it is accomplished? Well, you see, this time as we have done earlier, the focus of eyepiece and objective were coinciding at one point, but this time we are not doing differently. Means focus of the objective and focus of the eyepiece do not coincide at same point, and that means the image of a distant object, which is of course coming on from any object in lying in the space, and so the final image of the image formed of that distant object will be formed at focus of the objective. As you see, A1 B1 is the image of the object which is lying at large distance in space. This image is real and inverted. Now, since this image is located at a point which is less than the focal length of the eyepiece, therefore the final image, which will be inverted with respect to the original image, erect with respect to the image A1 B1, which will be virtual, and the distance of this object image A1 B1 from the eyepiece is so adjusted that the final image A2 B2 is formed at least distance of distinct vision. Means distance B2E is equal to D. Once this is done, our job is over. Now we shall like to find the magnification produced by the astronomical telescope when the final image is formed at least distance of distinct vision. We know, we have already seen in the previous topic, that magnification is equal to beta upon alpha, but for the small angles we consider tan beta is nearly equal to tan beta and alpha is nearly equal to tan alpha, and from the triangle, you see, from the triangle A1 A2 B2 E, we have tan beta equal to, these are same thing, so we have tan beta equal to A1 B1 by this distance FOE, and that is nothing but B1E. So we write B1E, A1 B1 by B1E. This is the value of tan beta. Angle B1E A1 is beta angle. So tan beta is equal to A1 B1 divided by EB1. And tan alpha will be, here you see it is the tan alpha is, you see tan alpha is A1 B1 divided by OB1. So A1 B1 divided by OB1, B1 is nothing but the location of the focus of the objective, so we can also write OFO, that is OB1. So finally we have written OFO as OB1. So A1 B1 by EB1 divided by A1 B1 by OB1, A1 B1 cancel out and it becomes OB1. This reciprocates divided by EB1. And from on applying the sign convention, what you see is OB1 is nothing but the focal length of the objective, and so we have FO with a positive sign. And you see another is EB1. EB1 is nothing but the this distance is measured in opposite you see this object, this image A1 B1 serves as the object for the eyepiece, and therefore the object distance for eyepiece is EB1, and that is negative, and so we have minus UE. But for lens formula we have 1 by V minus 1 by U is equal to 1 by F. So on putting the on applying the sign convention, what you have, this distance, you see, for the eyepiece we are applying it for the eyepiece. For the eyepiece, you see, V is nothing but equal to least distance of distinct vision. This is least distance of distinct vision, and so that should be negative. Image is formed on the side, we measure on this side we measure this distance against the incident ray, so it is negative, and UE is also on this side, means we are measuring it against the incident ray, so it is taken as negative, and focal length of the eyepiece of a convex lens we take it positive. So it means 1 by minus D, and here minus and minus both cancel it out, so it becomes 1 by E finally. So here we are left with 1 by E, and we carry 1 by minus D on the right hand side, so it becomes 1 by FE plus 1 by D, and that can be rewritten as, we take common 1 by FE, that can be written as, here we are left with 1, and since we don't have any FE, so we place FE in the numerator to carry the FE outside from this factor, so it becomes 1 by FE within bracket 1 plus FE by D. On putting the value of 1 by minus UE in this expression, you see F0 is already there, and that divided by minus UE, and for 1 by UE we have this factor 1 by FE. For 1 by UE we have this factor, so for 1 by UE we write it over here, and then with a minus sign, so we carry the minus sign, and then we carry FE outside the bracket, it becomes FO by FE minus, within minus sign FO by FE within bracket 1 plus FE by D. That can be also rewritten in the form of F0 within bracket 1 by FE plus 1 by D. While we write it in this form, it helps us understand that magnification is directly proportional to the focal length of the objective and decreases with, it is not directly inverse, nearly you can take it that it is nearly inversely proportional to the focal length of the eyepiece. So that we are now having the clear picture that magnification will be higher if we have greater focal length of the objective, and magnification will be higher if we have a smaller focal length of the eyepiece. This is all about astronomical telescope. In this case, you see, certainly the magnification is enhanced. If you compare with the previous case, you have seen that the magnification for astronomical telescope, when it is focused for infinity, means for normal adjustment, we have found that magnification was equal to FO by FE. And here you see you have this factor FO by FE, of course, but added to that is F0 by D. So that means more is the bigger value of FO, greater number will be added to the magnification of the telescope, which is having image produced at least distance of distinct vision. So certainly here we are having greater magnification. Now if we want to discuss the terrestrial telescope, we simply do is we create a situation such that the image which is formed inverted becomes erect. How it is done? It is very simple. Well, you see, one thing you must be remembering, that any object which is placed at 2f distance. Let us say we have some object placed over here which is at 2f, that means at the 2f distance from the convex lens, then certainly the image of that object will be produced at 2f, inverted and real. So if we introduce this system, whatever is shown in red ink, if you introduce over here such that the A1 B1 is placed at 2f of another lens which is introduced in between, then the final image which is inverted over here, the final image produced by this lens which has been inserted in between the objective and eyepiece, this is inverting lens. Now the image of this inverted this inverted image will be made erect and without changing any size of the image. So that means that image which is now erect with respect to the object will be enlarged, and then we feel comfortable to look at the earthly objects. One thing you must be noticing, that since the inverting lens is not magnifying or demagnifying the image, therefore the final magnification of the terrestrial telescope will remain same. The expression for magnification will remain same as the case may be, and usually in this case we make the image at least distance of distinct vision, and so the magnification expression for magnification will remain same. Only the length of the telescope, the terrestrial telescope, will increase by a length which is equal to 4f of the inverting lens. So you can please go through the more other details of doing the same job, means inverting the image by other methods, so that you have greater understanding of the terrestrial telescope. Thank you and have a nice day.